So the next I want to talk about is the E8 and then the E8 to 40 quasicrystal, which is a new concept. And then the 600 cell, I think you guys probably are familiar with it. It's which has the H4 symmetry. I don't think I'm going to talk about 240 polytope. It's the outline. So first I will introduce, I don't have to introduce, you guys all know E8 lattice and the Gosset polytope. And then I will talk about the E8 to 40 quasicrystal, which is also called Elser-Sloane Quasicrystal. And then the 600 cell and its rings. And I'm going to talk about this rings because this mapping is from the Hopf mapping. It might relate to Gerlis's models on the electromagnetism and the mass of the particles. So then, yeah, I will skip the last one. Okay, that's the Cox-Dinkin diagram of E8. And so E8 is an 8-dimensional diamond lattice, so which means it's 2 sets of FCC translated by 1/4 along the body diagonal direction. And FCC can be thought as the cubic lattice with all even dimensional facet centers. Just decorate the even dimensional facet centers of the Z lattice. And or every other point of the cubic lattice. And the nodes of E8 are first given by all permutations of these numbers, 0, and then there's this. You can see this is the even. This is a 2 facet, right? The center of 2 facet, center of 4 facet, center of 6 facet, center of 8 facet. Okay, so and the above set, that's a FCC, and the above set translated by 1/4 along the diagonal direction, and it has a total of 256 nodes. These nodes have been used to model the fundamental particles by Gerlis and Tony Smith and a lot others.
Can you go back?
Yeah.
I don't understand the first bullet point. How is the 8-dimensional lattice made from 2 3-dimensional objects?
No, FCC is 8-dimensional
The
FCC.
8-dimensional FCC.
Yeah. Yeah, it's a face-centered cubic lattice. Yeah, it's not 3D. Okay, so the Gosset polytope. And the first shell of E8 has 240 vertices, with 112 of them from the set 1. We just talked about there are 2 sets, right? 2 sets of FCC. So 112 can be from the first set, and the 128 would be from the second set, which is shifted by 1/4 from the diagonal direction, in the diagonal direction. So these 240 vertices from the Gosset polytope, which is a coordination shell of the E8 lattice, it is kind of the AD analog of the 3-dimensional cube octahedron. So the Gosset polytope's 7-dimensional facets are 17280 simplices, and then 2160 cross polytopes, which is analog of the octahedron. All smaller dimensional facets are simplices. So there will be, 60, 5D, 4D, 3D, 2D, all just simplices.
I should add, because I know you're interested, Mike, in sphere packings in higher dimensions. It's interesting to note that you can construct the E8 maximal sphere packing point set from the 3D maximal sphere packing point set. So it's you just rotate FCC lattices from one another, and you do an iterative process, and then you end up with the E8 lattice as a construct of FCC lattices in 3D.
All right, so to achieve the Elser-Sloane quasicrystal in 4D, it's really as simple as like a bending. It's like you have the AD E8, and you just kind of like fold it in half, like fold it halfway, right? And then so each of these fold would be a 4-dimensional quasicrystal, which is the Elser-Sloane quasicrystal. And then so this is like a the simplest cut and project method that I can find, the matrix, the mapping matrix is this. So it's very straightforward. You have all the points in E8, and you kind of select a layer. The cut and project window is defined as the Voronoi cell in AD. It's a dimensional, kind of cell. And then then you project that 8-dimensional Voronoi cell to the 4-dimensional. So E8, you want to project to 40. This is a 40 physical space for quasicrystal, and there is a 4-dimensional vertical space. And so you project the Voronoi cell to the vertical space, and that will give you a boundary to limit the point that has to be inside of this vertical window to be projected to the 4-dimensional physical space. And so then you use this mapping matrix.
Sorry, Fang, what's the property of H capital? So it's antisymmetric as other properties?
It's a cubic root of unit.
H capital. Right?
Yeah.
So how do you find it?
I don't know. For the direct cut and project method, it is explained in Elser-Sloane's paper, which I should give a quote here.
Yeah, I'm asking it to you because it's amazingly similar pi. How do you call pi capital?
Pi capital.
Yeah, pi capital. It's a 2x2 formal matrix, which is absolutely equal to the Freudenthal triple system element. The only difference is that H will be in the Freudenthal triple system a Jordan algebra, which will be a formal 3-dimensional algebra, 3x3. Instead, in this case, you have 4x4. I wonder whether there is some mapping between H capital and a certain Jordan algebra.
Probably yes.
Probably yes. If it is so, pi capital is nothing but a Freudenthal triple system. So you can endow. Okay.
So what you're kind of implying from something you said a few minutes ago is that even if you don't project E8 down to a lower dimension to create those quasicrystals in 3 and 4 dimensions and 1D, you can kind of recognize the same thing with just that irrational slice of the 8 dimension. So there's a sort of representation in that slice of all the information in the projection without even transforming it.
Right. Okay, so the main focus of this talk is I want to talk about this Hopf mapping instead of this direct orthogonal cut and project. So E8 can be thought of as the concentric 7 spheres, right? So the S7. And so, the first layer is the Gosset polytope. So E8 lattice can be decomposed into 4-dimensional FCC lattices. Okay, so this is to build up for the Hopf fibration. 3, 3, 4, 3, with the complementary lattice also being 3, 3, 4, 3. Okay, so there you can just think about a physical space 4 dimension and then a vertical space 4 dimension. Okay, so its coordination shell is 3, 4, 3, which is the 24 cell. And then the 24 vertices of the 24 cell are inscribed on the 3 sphere, right? So, so from there, the 240 vertices of the Gosset polytope are inscribed in a 7-dimensional hypersphere S7, and they can be split into equivalent subsets of the 3, 4, 3, each being an S3, which does not intersect the 9 others. So just these 240 vertices, which is S7, lives on S7, and it can be fibrated into these fibers of the 24 cell, which each 24 cell live on a 3 sphere. So like 10 fibers total, right? So 240, and so 24 for 24, each 24 on a 3-sphere. And so then these fiber lives in a 4-dimensional space.
And if I could add, Fang, so when you think about the 24 cell, the closest polytope in 3 dimensions that at least me and Ray agree is analogous is the cube octahedron. So sort of like, even though the cube octahedron is not regular, in 4 dimensions its analog is regular. And so when Fang says this, how you can take 10 of these and rotate them from one another to generate the 240 vertices, so we do the same thing in 3D where we take 5 cube octahedra and we just rotate them by that 15.5 and we generate the 60 points of the 20 group twist. So it's kind of, there's an analogy there.
Well, this is like talking about the other way. You have these 240 already, and you kind of split them into 10 sets of 24. Each 24 is a 3-sphere. And so, and these 3 spheres lives on the base of S4. So that is a Hopf fibration of from S7 to S3 on the base of S4. So that is kind of easy to understand.
This 343 is a Schlafly notation?
Yes.
Oh, that's what the Schlafly is.
For the axes of symmetry,
Yeah.
the symmetry, right?
Okay, so each 343 fiber of the Gosset polytope would generate a 3343 4-dimensional sublattice of E8. Right,
It's named the icosal tetrachoric honeycomb.
oh, okay.
Okay.
But anyway, so
Icosal tetrachoric for 24
Yeah.
honeycomb.
French?
It's English.
It's English. It sounds like French, but
It's English with a French accent.
Icosal tetrachoric honeycomb.
wow.
yeah,
it
just
comes
like
from Greek, naturally.
just like a cuboctahedron, right? It's a kind of a shell polytope of a FCC lattice. And so here, the 343, which is 24 cell, it is a shell polytope, or just like the Gosset polytope to the E8 lattice here. And so this 24 cell, you can extend it, to generate a 3343 4-dimensional lattice. That's
Right.
clear, right?
Or you could say the cube octahedron is just the root vector polytope of the maximum sphere packing lattice in 3D, right?
Yeah. Okay. So then it's clear that there are 10 such equivalent sublattices because we have 10 of these 24 cell fibers. And so passing through the origin and labeled by 10 points on the base S4. Okay. And then consider the point P on the base S4, right? Okay, so consider the point P with coordinate this guy. So it is, the S4 lives in the 5-dimensional space, right? So then just think about the S4 in a 5-dimensional space and think about in 5-dimensional space there is this Z5 lattice there. And then take the direction that is diagonal of the 5-dimensional cubic lattice, where this S4 lives in, right? So just take that diagonal direction, which is this direction, and then that's where the P is at. This is origin, and then this is the P, and this is diagonal of the Z5 lattice, and this is the S4 sphere. So imagine that. And then so it's equivalent to 5 of the 10 base space vertices. It's equal distance. So that's the point P, and then this is the origin, and this is the whole sphere. And so from the point P, and so we have 10 fibers on the S4, right? So the 10 S3s. The 10 S3, there are 5 S3 equal distance to the point P. And there's another 5 that is a little bit further away that are like right here. So it's further away from the P. Okay, so then now the next step is from the point P, we can map each of the 3 spheres. This is 24, and then we map it down. So we map these 5 down from point P. That's a projection direction, literally. You project it from that direction. And so you got a 600, a 600 cell. So 5 fibers, right? 5 times 24, that's 120 vertices. Now become a 600 cell. And the other 4, which is a little bit further distance, would be mapped to the smaller 600 cell. Okay, so now you can understand from the E, the polytope, and then we actually mapped to 40 two concentric 600 cells. And then,
Yes.
yeah,
Scaled
so
by
golden
the
ratio.
Scaled by the golden ratio, big
Yeah.
one, small one.
And then it is a very symmetric, you know. And then so,
Is that the two equidistances then? One is the
Yeah.
golden ratio, one is the universal.
mhm.
I don't think so. Can you hear his question again?
You said that the equidistance, yeah, 5 of the 10 is equal distance to that point.
Before you project
There are
it.
two equidistances, no?
Yeah, each
What's the
one,
the
yeah.
ratio between the two equidistances is the golden ratio.
The
ratio-
distance between them.
You don't get the golden ratio.
difference.
The equidistance
ratio
in her
of-
first instance, she's talking about before the transformation, so the equidistance, she's talking about on the Gosset polytope. But then when you transform them by projection to 40, that's where you get the spacing between the two and the size between the two
Yeah.
becomes golden ratio related.
Yeah. So that equidistance, I don't
Which
think that's.
relations? Do you know which relation?
The size of each 600 cell is one to the other as golden ratio.
Exactly.
Exactly.
Yeah, yeah. So they mapped in 4D to different sizes of 600 cell. That's a golden ratio. The two distance, I don't think that's a golden ratio.
The absolute value is not a golden ratio.
Now,
I think it's a projection, which is a cosine of the. So you have a distance. Basically, it's like, I don't know if I can write on here. It's like, you know, from here, it's like you project these points like here, and then there is the point here, and you project these points here, right? So then this is R1, this is R2. So R1 over R2 is golden ratio. But the distance, this is a D1, and this is a D2. So you can see they are not really like proportional to each other.
Yeah, it's more complex, the
Yeah.
relationship. But, so are you drawing?
Yeah. So yeah.
Oh, okay.
So this is a P. This is a distance 1. This is distance 2. Right? And this is a projection. You know, this is length 1, this is length 2. So this is the golden ratio, but the other one is not.
so in other words, you don't really get the golden ratio until you break the symmetry of E8 or the Gosset polytope by this special projection vector that is deeply related. That projection vector is very deeply related to the structure of E8, and it is, of course, the only one that brings you to a root vector polytope in your projective space that's regular.
Yeah. So far we're talking about the first layer of the E8 lattice, which is the Gosset polytope, and we transformed it to 4D into 2 sizes of 600 cells. And so then the next thing we want to go to the second layer in E8. We do the same thing. We go to the 3rd layer, 5th layer, right? So we do more layers, and then in 4D we also have more layers. So, and then but in AD we have to have a selection scheme. We have to select. We can't have the whole E8 lattice, right? We have to select the points in E8 so that we have a 4-dimensional quasicrystal that is not dense. You know, it's not like if we project the whole E8 lattice, all the layers, then in 4D it will be black. So we have to have a selection scheme, and then so that part. Let's see.
And may I add 2
Yeah,
comments?
sure.
The slide before, please.
Oh, okay.
So just the 10 points on the base S4, so they are not random naturally. They make a regular polytope in 5 dimensions, which is the cross polytope. And
Cross
polytope, the octahedron,
Cross.
hyper octahedron cross polytope.
Okay.
And so just the coordinate are one of the 5 is +1 or -1, and the other are 0.
Right.
It's regular. Yes.
So the principle obviously is that we're taking, we're hoping to use, any good mathematics that's been developed in sort of fiber bundle theory and fiber theory, and we're trying to discretize in two ways. We discretize the number of fibers, and then we discretize each fiber with a finite set of points on the fiber.
And my second comment is that the number of points that you have on each additional layer is linked to number theory
Yeah,
and to
the fabulous. Yeah.
to the theta function linked to the number of divisor of some power of prime number. So this is really linked
Why?
to
The prime
all
number
the result
is deeply
of
related
number
to prime
theory.
number
How
theory.
does it relate?
I think it's beyond,
No.
to
Okay,
explain
so-
to them, it's beyond the scope
That's,
of, but
I can give you this
Sure,
after
it's
the
really interesting
presentation.
though, how it
After-
ties into
It might
prime
be
number
connected
theory,
through the
with
torsion
all of this.
Yeah, the
Number of
data
divisors
functions
of,
are related to L functions.
Yes.
L
In my
function,
hypothesis,
Yeah,
Yes, yes.
that's where we want to be.
and so there's a paper that really Ray and Carlos did all the work on. It's this beautiful paper that draws out this really interesting correlation to prime number theory and quantum mechanics. That when did we publish that? Last year, right? Yeah.
Yeah.
What's the
This
concept?
fibration of E8 was this by Sadoka Masori?
Yes.
Okay.
Yeah.
Okay. It's good that you're getting the reference. Of Sadoka
Yeah,
Masori.
that's something that I forgot. I
Yes.
should give you
Yes.
guys the reference.
Yes.
And so they actually went on and then did lots of discussions on number theory part. Yeah.
Yes, it's
Because
in the book,
Sadoka
in
Masori
fact.
also wrote a book on geometric fractions.
Yes.
Yeah, they
The same
I think
people?
they invented
Yes.
the word.
Yes,
No.
they're
Yeah,
the
the
same
same
people.
people.
Yeah.
They may have coined that term, geometric
Yeah.
frustration.
Yeah.
Don't think
So
so,
it's
but they used
Sadoka
it in
and
this
Masori?
sense, so that's-
Sadoka
Okay,
Masori.
Sadoka Masori, right?
So,
Yeah.
Yeah, because he wants to write it because it's
Is it Masori or Moseri?
Moseri.
Moseri.
Like, more like what you said.
Yeah. Okay, so I don't know if I can finish this within 2 minutes.
No, it's okay. We can go past.
Yeah, so this is just talking about the two orientations for a hopeful mapping. Can be like a crystal mapping or quasicrystal mapping. And then crystal orientation, like you can have the E8 or E8 that is the same orientation and then do the four-dimensional thing, do the Hopf fibration and everything. And then, no, but the C orientation is like, okay, you have the E lattice, don't rotate it. It's just like, and then you have the 4D, which is made by the E1, E2, E3, E4, right? You project it to this 4D, of course, that's a crystal. But if you wanted to project it to the quasicrystal orientation, you rotate the E lattice in such a way that the four-dimensional plane, which the hopeful maps onto P, is now hopeful mapped in onto this point. So it's like you rotate the E8 so that one of its lattice, the base vector would be aligned with the P, the diagonal direction, the Z5 diagonal direction. Just like instead of you keep the E like not changing and then try to do kind of this mapping into this P, which is like a 1, 1, 1, 1, 1 direction. You literally just rotate the E8 so that you can project the whole thing into the E1, E2, E3, E4, that kind of space. It's like instead of taking a regular, a lattice and then project it to an irrational direction, now you just rotate the lattice to an irrational direction and project it to the kind of like a rational direction. So that's just a method.
If I could add to that, another way to think about it is, if you were to just take a projection vector relative to one of the axes of symmetry of the root vector polytope, you would actually lose information and you would just project down to a simpler crystal and its algebra. But if you take a substructure of E8, like Fang mentioned, Z5, and how I showed in my presentation how you can construct it with tetrahedra as a lower dimensional substructure, and when you look at those rotations relative to one another, you get all those golden ratio numbers. So our projection, or really not ours, Elser-Sloane's projection vector is really deeply related to one of the completely different set of angles in a lower dimensional subspace of E8.
I would add also why we project along this precise direction, which is the diagonal direction. So this is because the diagonal direction is the natural projection for an object whose coordinates are a circular permutation of one set. Like here it's 1 or plus 1, 0, 0, 0 or minus 1, 0, 0, and the permutation. So then you have to project along the diagonal, and it's worse for many regular polytopes, 24 cell, all the 600 cell.
To me, it's the most symmetric direction when you do the Hopf fibration, right, from S7 to S3.
Yes, so it's because the coordinates are expressed as a circular permutation of a set of numbers. In the basis space, then the natural projection is along the diagonal of this space. This is general. So this is not arbitrary at all to choose this direction.
Yeah, definitely it's not arbitrary. Yes. So these are the three references. I just copied it from the top of the paper, so it's not in the right format, but the first one is Elser-Sloane's paper. He first talked about this quasicrystal cut and project from E8. He gave the mapping matrix, and then Sadok and Morseri talked about this shelling. Yeah. And then
No, sorry. Not with the Spanish accent.
And then Moody and Petro, I think they also did discuss it a little bit further. I think about this shelling of the E8.
Yes, they find errors and they find the exact formula.
Yeah. Okay, so just to review, this morning I covered this from E8. E8 has the 7 spheres, the shells of the 7 spheres. And then so for each shell, we can do the Hopf fibration, and then so we get the S3 fiber, which is 24 cell, and the base is on S4, and then S4 lives in 5D from the 5D. Imagine 10 points on this, and 5 here and 5 here, and then there is another direction there that is the 1, 1, 1, 1, 1 direction, and so we can then map these 5 fibers into a small 600 cell and another 5 into a bigger 600 cell. And after we get the S3, right, the 3 sphere, and we can go further the Hopf fibration, which we'll talk about later, which is this part, but we will talk about this part later. And first, I wanted to kind of mention about this acceptance domain, which is like what I said. You cannot project the whole E8 to 4D because then you get a black space, like, too dense. And so you have to have a kind of a window to select which fiber to project to 4D, right? So then that's called the acceptance domain. So to be simple, to not go through all these, and then you can read in a book, and then so the acceptance domain for this is really just a 3 sphere, in a vertical 4D. You select everything that is on the 3 sphere. So then you select all the fibers on that, and then you project, and that's the 4-dimensional quasicrystal. And so then this is quasicrystal. As far as I know, all of them, they're self-similar. So here, each point is okay, so these are the points in the 4-dimensional quasicrystal, okay? So then each of these red sphere is a 600 cell in the 4-dimensional quasicrystal because it has 120 vertices, okay? So if we take each 600 cell as one vertex, and so this whole thing becomes another 600 cell. So it's self-similar. So you shrink each 600 cell to a point, and then this point and then these other 600 cell form another bigger 600 cell. It's self-similar.
So from here, the center sphere sphere,
Mhm.
central sphere,
Yeah.
is a 600 cell,
Yeah.
as are all the other spheres
Yes.
in red and pink.
Mhm.
And you said there is a bigger 600 cell, which is the whole thing,
Mhm.
right? But is the second ring also 600 cell?
No, this whole thing, it looks like a second ring, but they're all equal distance to the center one. This is just in 2D, it looks like this. But
Right.
if I would rotate it, all the spheres are equal distance to the center sphere.
Ah, okay, so
Yeah.
this is a 2D projection
Yes.
of a thing.
Mhm.
And what is the three-dimensional polyhedron which is projected here?
That's 600 cell, right?
600
No,
cell
three-dimensional,
projected to
please.
that, it's a RT.
RT, okay.
What
Rhombic
is RT?
tetrahedron.
Russian.
Rhombic tetrahedron.
Oh,
This guy.
This?
So this is the projection of 600 cell.
Yeah.
Yeah.
This?
But that's,
No,
that's,
the RT is there.
that's many 600 cells.
That's just
No,
the central
this is the
one.
one 600
No,
cell.
no, that, what Ray's saying is what is the projection of that?
Yeah, but for each one, I would say.
Yes,
it's not
each one.
For each one.
The
yeah.
center, for example, this is a three-dimensional polyhedron.
Mm-hmm.
It's
Yeah.
a 600, it's a, oh,
It's a RT or
oh yeah, what is,
Yeah,
oh, that's that.
yeah, you can see that it has these facets, and then
Oh, a
it's
rhombic
a
rhombic tricontohedron.
yeah, it is a rhombic tetrahedron. I figured this. I think it is on the same plane. Is it?
Which is
No.
the supercell and the root vector polytope of the 3D Penrose tiling, the Amman tiling.
I think I plotted out on the 600 cell, like the most outer layer, it looks like a rhombic tetrahedron. I mean, I can double check on
But
that.
I'm still a little confused why you call this
It is.
self-similar though. I
Well,
understand that there are identical 600 cells which are equidistant from the central 600 cell. That I understand.
yeah, but I'm just saying like each 600 cell, if you shrink it to one point, and they become the vertex of a bigger 600 cell.
Ah, okay.
You know?
So one thing that's a technical thing here is fractals, like the Mandelbrot set, are a fractal because they are self-similar in shape, not self-identical. Crystals and quasicrystals, on the other hand, are not self-similar, they are self-identical in shape at all scales. So I would use the word self-identicalness.
Yeah.
Doesn't sound as good.
So Ray, to answer your question, see, this is a real quasicrystal, real life quasicrystal. It has dodecahedron shell, arcasa dodeca, and then it has this rhombic tetrahedron cell. And similarly, in this is a 600 cell that I projected. So there's arcasahedron, dodecahedron, and then arcasahedron, then arcasadodecahedron, and then it's the RT, rhombic tetrahedron.
Okay, this
And
is
by the way,
this projection.
that here is what I was sharing with you at lunch in the
Inside.
tie-type quasicrystal, shell 1, shell 2, 3, 4, and then on the inside it violates the symmetry of all three of these are icosahedral symmetry, and then that one is the lower symmetry, so it gets confused as it's trapped in the middle.
Okay. So next I wanted to talk about the further Hopf fibration from the S3, which is the 600 cell, and its rings. So actually there are two ways of fibrating the 600 cell. We can do like a 10 decagonal rings, 12 decagonal rings, sorry, or 20, I didn't say this part, it can also be 20 hexagon rings.
Right.
Yeah, 20
But they
hexagon.
would be on the same plane as the others, so the decagon's a good way, because it's on the same plane.
They're same thing.
Yes, I know.
Yeah, it's not, the hexagons are also on the same plane. Each hexagon.
Right, but
becomes a
each
ring.
of the decagons is on a different two-dimensional subspace.
Yes, same as the hexagon.
Yeah.
Yeah, they're equivalent ways. So, and then from these 12 decagonal rings, we can actually have 30 tetra rings. So it's difficult to really imagine it. But this is 600 cell projected to 3D, and then you can see these are the decagonal rings. And each three of the decagonal rings, not all any three, okay, you select the three that some threes that can form a tetrahedron rings. Like these are made of tetrahedron volumes. And so there are 30 tetrahedron there. So I'm going to show you a mathematical notebook on that to get a better idea. So you can see that the 600 cell can be split into these fibers, and they're not intersecting, and they're not linked. Oh, are they linked? They're not linked.
They're not. None of them are touching each other, right?
No, and they're also not like this is linked, right? So they're all separated. So, and then we could select 3 of them to make a tetrahedral ring. So see, this is one of them. One of the ring. 3 of the decagonal ring form a 20 tetrahedral ring. And there are a total of 30 tetrahedral rings. Yeah, there are 20 of them. This is another one.
Can you share the periodicity of those?
No, I didn't prepare that part.
So I'll share. So each of these, I want to connect this for you guys to something I claimed yesterday, which is that the QSN is a more powerful code than the higher dimensional Elser-Sloane, because one of the things it does is it allows you to alternate between 3 and 5 periodicity, whereas in the 4-dimensional case, see the red, we need to keep that red thing. So that's closed. All the tetrahedra are regular. Each tetrahedron is rotated from the other by this arc cosine 1/4. But if you ask, well, what is the periodicity of it? It's both 3 and 5 periodicity. How would
you can't say it that way
you say it.
simply.
You say it.
Well, if you look at the periodicity of their centroids, it has a 3 and 5 component in it. You could be like, you skip every 5, and then the centroid is like the same kind of relative location, and then, or you could be skipping every 3. I mean, not skipping 3, like skipping 2, so every 3, and then they landed on the same relative location relative to the center, like the same distance from the center and same height. This is a plane. So I can only say that. But the tetrahedron, if you look at the periodicity of the tetrahedron, including its orientation, then it doesn't have a 3 and 5 periodicity.
Right. So it has it in that way, and we think that then that gets translated into the QSN in that representation in a code-like manner where you have code freedom to manipulate the 3 and 5 periodicity.
Which is related to the phylics, because I wanted to mention about that. If you put a tetrahedron like one after another and then make it like a long string like that, right? There is no periodicity because the irrational angle of the tetrahedron. So that's called a BC helix. Yeah, so there is no periodicity. But if we rotate the tetrahedron that next to each other with this kind of rotation between their faces, so keep their face center fixed and then rotate them relatively. So if we do that,
rotate them in the same direction, she means, of whatever the helix direction is.
Yeah, so if you rotate each adjacent tetrahedron, and all of a sudden this tetrahelix becomes periodic.
5.
It can have 5 periodicity or 3 periodicity, depending on, because the tetrahelix, if you don't rotate the tetrahedron, and it already form a right or left helix. So if you rotate if it's a right-handed, if you rotate the tetrahedron also, to the right, like make them right-handed, and then so that will give you 5 periodicity. If you rotate the other way, it gives you 3 periodicity. If you look down, and then you look at the tetrahedron, and so literally it forms either 3 or 5, depending on which way you rotate it. But there is only one rotation angle, which is this angle, which is this 15.5 degree. So that is related to this, because this is a projection from E8 to 4D. And then so when you project it to 3D, it looks like this, right? So in 4D, they're all regular. It has this 3 and 5 kind of thing already in it, which is kind of like talking, already saying about the 3 and 5 periodicity. But if this is with discrete curvature, right? Because in 4D and between tetrahedron there is a little bend. If I don't use the bending, I can use a like a little fold, you know. And so then if we would translate that down in 3D to the twisting, like I said, the geometric frustration, right? If we, instead of curving them, let's just do the rotation or the twisting between the tetrahedron. So we do this kind of twisting, and so it can translate again to the 3 and 5 periodicity. So instead of a ring like this, and then using the twisting method, you can see a tetrahelix that relatively rotated like this between each tetrahedron facet. They also close up this 30 tetrahedron ring circle, and in the meantime, it has this 3 and 5 periodicity in it. So yeah, it's
And so the ability to manipulate that comes from the geometric frustration. So here in 4D, where there is no geometric frustration, it's just these alternating 3-5 periodicity where you really can't encode information because you don't really have the opportunity to rotate. So the code of the QSN sort of gives you that. I don't know if we can use it for anything, but it's there to use.
yeah. So that's why, you know, the next I'm gonna talk a little bit about some suggestions of using these for physics modeling, and then after that I'm gonna move on to QSN. QSN, everybody already talk about QSN. I don't know how much you actually know about QSN, but I'm talking about how to generate it, and then how do we do the coding there? How does it even relate to the Elser-Sloane Quasicrystal? You know, how we want to do the coding here. I have another notebook that just to show you. You know, this is the ring we talk about. And so around each tetrahedron, you know, like if you find the surrounding tetrahedron that share something with this central tetrahedron, right? Either vertex or edge or face. So then you get the 56 around it. So together it's a 57 group. I shouldn't call it a group, but probably it's 57 tetrahedron. So then as the tetrahedron moves to the next on the ring, you can see this 57 tetrahedron move. Like, you know.
So as you think about this, it's very distorted because of how we're projecting it to 2D, but if you see this animation, you see how the walk of this 57 group, it's rotating. So it has the symmetry of a tetrahedron, this 57 group, and it rotates at the same time that it helically propagates forward. And that's this intuition on this electron clock model where you need a spherical rotation stepwise and a helical forward propagation.
For some reason, it just reminds me of like the Hoovis helix thing.
It's a tetrahelix, right? Looks like a tetrahelix.
Or even like a Mobius strip or something like a quantized Mobius strip.
Yeah.
It's a three
is.
surface
Yes. If you follow one surface, it is a Mobius strip. If you follow, because there are 3 surfaces, right?
It's a each
So
one is a
you
Mobius strip wrapped
follow.
around the other, a discretized Mobius strip.
Yeah.
How many of them?
Okay.
3
only one?
of them.
So there's three two-dimensional bent. Each two-dimensional Mobius strip is folded like origami, according to tetrahedral facets. And each one of these 3. This here, like Fang was saying, these are just 3 regular decagons rotated each from the other on a shared centroid, each one into another 2-dimensional plane in this 4-dimensional space.
How are the 3 Mobius strips interlaced?
Yeah.
Yeah,
Are they knotted into each other, or
Would you call them
Uh,
knotted?
let me-
are
let
they
me,
one inside?
they're not. I don't think they're knotted,
Is it
but let me.
Hopf? Is it?
It's like a Hopf fibration.
Of them.
It's 3 discretized Hopf fibers as
So
3 decagons.
The 2x2 Hopf.
Yeah.
Yeah,
Exactly.
like here you can see there is a one that is here if you keep following, and then it goes around, and there is another. They are like sharing one edge. almost going around. So there should be like a, it's like a threefold. There's three of them are kind of always like, these are two, and there's a third one. They kind of walk along with each other like that.
So the non-trivial question is, are they making a trefoil knot, or are they independent?
They're independent because they don't, right? Aren't
They're not linked. I don't know if
They only share a centroid.
like they're not intertwined like this.
They are not
It's
knotted.
like taking two circles with the common centroid and then rotating one into the second dimension while it maintains its centroid position. But there's an analogy here. Can you, when you go, if you
Yeah, like
They
here you
continuously
can see
deformate-
none of
they
these.
continuously deformated one from each other.
Yeah, so none of these
without the break,
none of these rings are
intersect,
intersecting, but the
but they all share the same centroid.
the ribbons,
To be confirmed.
yeah, anyway.
So can I just give a quick analogy? So here's the 20 group, and then I'm going to make an analogy with this 600 cell. So you can most simply think about the 600 cell as 10 decagons. And you can very simply think about this as, if you want to relate it to a semi-regular polytope, is where these edges cross, dividing these lines into the golden ratio, you have 30 edges forming exactly the icosahedodecahedron. And you can think of the icosahedodecahedron as half of this, in a sense. Where this is 10 decagons, the icosahedodecahedron is, Fang, tell me if I'm right, 10 hexagons. So 10 hexagons that share points, so every time, like my knuckles sharing, so 10 hexagons, 10 decagons, all sharing the same centroid and rotated from
So
one
that's
another.
a 6 decagons.
Right. So yeah, six.
6 decagons.
6 decagons. 6 times 12 is 6. Yeah. Fang's right. 6 decagons, each sharing a point at an intersection, leaving you with only 30 points, describing the icosahedodecahedron.
Yes.
This is inside the QSN.
That's inside
Yes,
the.
this is.
When you do the QSN, do you give direction to the graphs connection, or there's no parameter you use to give a direction?
There is the direction of the symmetry of the QSN itself, so there are directions according to the root vector polytope, which is an icosahedodecahedron, and then all of the spin actions or Clifford rotors that you can operate your phazon dynamics to change the connections in the possibility space of the QSN. Those are, those would be these.
So this is a representation that comes from low quantum gravity approach. So when you put the 6J symbols on the tetrahedrons, do you know how they orient? For example, these are Mobius bands with two borders, right?
Yeah.
Do you know if the J's go one in one direction, the other? Did you have an intuition of the mapping?
In 4D? You talk about in the Elser-Sloane or in the QSN?
Wherever you, in QSN, I know you can match the angular momentums to the size of the tetrahedron. I don't know how you could do it
I don't think we have that intuition
We haven't
yet, but
well,
most of us around here are suspicious that this physics on the QSN is going to deeply relate to the plane in the code with the chirality. So there will be a chirality sign value that's foundational, and then there will be a second sign value which is called periodicity, where information is encoded by patterns of 3-5 periodicity.
So I'm asking you if the Mobius bands
Yeah.
are if you know Escher's Mobius bands, is it number 1 or is it number 2? So do the border go in the same direction, or do they go in opposite direction? Like the DNA
Right.
extraction.
I don't.
You could probably map between them.
Yeah.
But this will be this T-duality of. There's a world sheet, discretized world.
So we haven't mapped it and we haven't
It's
worked on it, but I can only speak for myself and say that I expect that to have some deep importance in the physics, and at least Fang is a agreed with me that whether we use it for physics, math, or not, this, what she described, where there's an inherent, what Carlos just called a tetrahelix, which has no periodicity, and then in the QSN, you never find that, but you find these helices, which can be spaced, like the tetrahedra don't even have to be next to each other, but then how they're related will have this 3 and 5 periodic relationship.
And trying to map to
but we think that it would be silly to ignore that, because if it's such an inherent part of the QSN, why wouldn't, in nature used the QSN, why wouldn't she use that 3-5 periodicity for something meaningful?
Yeah,
you know?
So strings in string theory do have a Mobius strip worldsheet sometimes.
Okay.
So that's already known, but to have it discretized, that's a more interesting question. Because that's essentially, if from that approach, you have discretized worldsheets and discretized world volumes.
Mm-hmm.
So it's different than a spin network,
Mm-hmm.
because this is, you actually, you have a matrix system,
Mm-hmm.
and you have a precise meaning, and you know the spins, and
So this is just some conjectures here. I just talked with Marcelo a little bit about how do we model, physics using this Hopf fibration. And so, just again, there's 12 decagonal rings, or fibers, there's 20 hexagonal fibers. And then in the Gosset polytope, Remy Masseri, he talked about the 60, rings that are like actually squares. So, and then in the 40, it becomes like 30 of them, right, in 600 cells. So 40 is 30 squares. But I didn't check on that. So then we were thinking, okay, so just think about these rings as the states. So then they're like, in his paper, he's talking about their entangled states. So then we can select the on and off, But that's like what he was doing was using it for the quantum computation. So, but because of this hopeful mapping method, so we were talking about an action, this hopeful action, we could call it, from E8. I didn't mention it, but in E8, if there is a one point on a fiber that is selected, the whole fiber will be selected and projected. So it's like either there is a whole fiber or there is none point on that. So then these kind of like the way of selecting these fibers to project it down. So we didn't get it worked out, but we were trying to kind of write in the Lagrangian, and then so using these kind of actions. So each cut and project or selection of the fiber can be thought of as an action. But that part, I don't know, Ray, if Marcelo would be presenting something at a conference or something. So, but that's as far as, our couple discussion with him.
What are the discrete fibers on the Gosset polytope?
On the
In
Gosset,
the same way that we're talking about the discrete fibers in these 3D and 4D shapes, what are the discrete
it's S7, right?
I'm asking about the two-dimensional polygon. What is the two-dimensional polygon that can be used to rotate several copies and
It can be
construct
squares.
What's the maximal one, though? Meaning on one two-dimensional plane in the 600 cell, because you can do the 600 cell, by the way, with equilateral triangles or hexagons, but the maximum is decagons. So what's the maximum to generate the Gosset polytope? It has to be a two-dimensional regular polygon.
If it's S7, right?
Yes. Well, he's talking about the two.
You have to have some. No, is a tone. Is Has to
No,
be
but it's
Octonian
projected
discrete.
onto the
It's like Hurwitz number on Octonian.
It has to
something
be a
like-
polygon.
something
It
like
has
that.
to be a regular polygon, and I would guess that it's 20 regular.
It does not have five-fold
decagons.
symmetry there in E8.
Does that what?
No, it does not have a planar five-fold symmetry there. So it can be 5 or 10 or multiples of 5. So it can be multiples of 4 probably. 7?
Well, it's
You're
200.
discretizing S7.
It's
So if
240.
you're using the Fang plane representation for Octonian, 7.
No
and
projection.
You have to find the sum
Do
discretization.
you have an intuition on that question? Do you understand the question?
I don't
Yeah.
understand the question.
Just like,
because
okay, so there
for
is
me
a
it seems
E8.
that this is what
But
Fang
for
has
unity in
presented.
S7.
No, no.
So
Okay,
what is the difference?
Ray, there is a E8 polytope, right? It's on a 7 sphere. If you slice it through its center to make a slice, how many points can be on this slice? Two-dimensional
What
slice.
is the dimension of the
2D,
Ah,
two-dimensional
the
slice.
plan, it's 30.
Yeah.
This is the
That's right.
triacontagonal
That's right.
projection.
Yes.
It's a two-dimensional slide.
So, but it does not have five-fold symmetry for E8
Yes,
polytope.
because it's 30.
Actually, I don't know if it's 30.
30 will
I
have the
don't think it's
I don't
30.
think it's 30. 30 is only showing up in the projection where you force certain points to be on the same ring.
oh yes,
No
it's a projection.
projection.
You,
They have to be
you
the
take a
same.
slice. Okay.
Yes.
Yeah.
Ah yes,
I
not
think,
sure.
I think intuitively it should be the same number. You should be able to because you can do this with a regular or semi-regular polytope in any dimension. And so there certainly has to be a solution, very simple number, and it has to be some integer divisor.
Well, definitely
into
4.
240, right?
Definitely 4. I don't know if there's 8, but definitely there's 4. Okay.
Yeah.
So I don't know if you guys have familiar with. This is Lisa's one of his pictures.
Who's?
Gary Lisa's.
Uh-huh.
Yeah. So he's modeling this. I mentioned it before. Like these kind of winding around that ring. It's that's the electricity, like charge, and then I think these windings are the mass. So I'm trying to connect to these tetrahelix rings in 600 cell. So do you know?
It reminds me of some stuff I was doing with like topological deformations or the superfluid order parameters where they were deforming. You have the ring and then it deforms and you get that like in the one on the right, you know?
Yeah, but anyways, so he has this.
This is a new age de Broglie.
Yeah, New Age de Broglie electron clock, right? Yeah.
Yeah, so I just read it, on a Wikipedia page about him, introduction on that part. He's talking about, that's why the electron charge can have only like this, thirds, right? Like a 1/3 or like a 2/3 and a 1. So depending on it's like the integers of 1/3. Because it's 3 ones there. Anyways,
It's discretized.
it's discrete, yeah.
Somehow, so there's
Yeah,
like
because
a hexagon or
yeah, because it has to close. Yeah. So. So I don't wanted to talk any more on this. So I wanted to move on to the QSN, which is besides the Elser-Sloane Quasicrystal in 4D. So then we moved it to 3D. Like instead of the curvature, we wanted to use the twisting.